We have, let's compare sodium versus, let's compare sodium versus chlorine. So if I wanted to draw my Bohr's model for sodium, I know here's my nucleus, 1 ring, 2 rings, 3 rings. So 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, and 1. So here's sodium. Let's do the same thing for chlorine. Nucleus, 1, 2, 3, 4. Okay, so we know sodium has only 1 electron on its outermost shell. It has 1 valence electron. We talked about this last year. Is it going to be, do I need more energy to remove this 1 electron, or would it take more energy for sodium to gain 7 to become stable? So it take a lot more energy to have sodium gain 7 to become stable, right? So sodium actually really wants to lose this 1 outside electron, this 1 outer electron, because if it does, if it removes that 1 electron, what's it left with? A full outer shell with 8 valence electrons, and that's what it wants. So because it wants to remove that 1 electron, it is so close to becoming a noble gas, because if it removes that 1 electron, it would have a noble gas-like electron configuration, and that's what it wants. So sodium really doesn't need a whole lot of ionization energy to remove that electron because it already wants to do that. Let's think about chlorine though. So they're in the same energy level, they're in that same row, right? Well, chlorine has 7 valence electrons, so it only needs 1 more electron to fill that outer shell, and that way its electron configuration can behave like a noble gas. So in terms of chlorine ionization energy, does chlorine want to give up any of its 7 valence electrons? Absolutely not, it doesn't, because it only needs 1 more. It actually wants to gain 1 more electron. It doesn't want to remove any at all. So the ionization energy for chlorine would be so much greater because it doesn't want to lose any, it wants to gain 1 more. So because of that, ionization energy for chlorine is huge. If I think about the noble gas then, argon, all noble gases, since they have a full octet, do they want to remove any of their electrons? Absolutely not. So their ionization energy would then be the greatest because they don't want to remove any at all since they have that full, stable octet. Okay, so in terms of ionization energy, we're removing an electron here. So I have sodium. If we remove an electron, then that means we're going to get that positive charge. If I have sodium cation here and I remove an electron, I'd have an even greater positive charge. Okay, so ionization. When all valence electrons have been removed, we can say then that the ionization energy is going to take a quantum leap. It is going to take a quantum leap. Well, what does that mean? What does it mean to take a quantum leap? Let me think. What does that mean? What does that mean to take a quantum leap? Well, it requires more energy to remove each successive electron. And I want to show, according to this table here, it is important to notice that there's a huge increase in ionization energy when an inner shell electron is removed. So let's look here at sodium. So this I1, I2, I3, I4, so on and so forth, that just means first ionization energy, second ionization energy, third, fourth, fifth. So that means first ionization energy would be where I'm removing the first electron. Second ionization energy would be where I'm removing the second electron. Third ionization energy is the third electron, so on and so forth. So sodium, it takes about 496 kilojoules per mole of energy to remove that electron on that outermost shell of sodium. But remember, sodium only has 1 valence electron. So I don't need a whole lot of energy to remove that first electron. But then sodium would be left with this. It would have that full outer ring. So now if I wanted to remove a second electron from sodium, it is going to take a whole bunch of energy to remove one electron here since it's already stable. And that's what this table is trying to show you. So that first valence electron was really easy to remove, 496 kilojoules here to remove. That second electron to remove, 4,562 kilojoules. And it's going to take a bunch of energy because once sodium loses that one electron, it's stable. It has that full outer shell. And now I'm messing with that full outer shell. So it's going to take a ton of energy to remove one of those electrons. Magnesium, same thing is happening. For magnesium, it takes about 738 kilojoules of energy per a mole of magnesium here. So 738 kilojoules to remove the first electron, 1451 to remove the second. But then once those two outer valence electrons of magnesium are gone, so once we're at that second ionization energy, magnesium then has accomplished its noble gas electron configuration. So now, when I'm trying to remove a third electron from magnesium, it takes 7,733 kilojoules of energy to remove that electron from that inner shell. So once we start getting to these inner shells, we see that there's a huge leap in ionization energy. And we're making a quantum leap because once sodium loses its one electron, it's now thought of as having just two energy levels instead of being on the third energy level. Same thing for magnesium. Once magnesium loses its two valence electrons, we've now made a quantum leap. We've gone down to a different energy level. So that's considered our core electrons. So it's going to take a lot more energy to get rid of those core electrons. So that's what this table is trying to show here. Okay, we have three elements are indicated in the periodic table below. So we have three elements that are highlighted here. I want to know which one has the largest second ionization energy. And I'll give you a minute to kind of look at this and maybe come up with your answer. Which one has the largest second ionization energy? So remember, first ionization energy would be removing one electron. Second ionization energy would be removing two electrons. Third ionization energy would be removing three electrons, so on and so forth. Okay, well, let's talk this through. So, my little orange box, or my little red box here, that red box represents what element? It represents sodium. And we know sodium has how many valence electrons? Has one. So sodium has one valence electron. So if I went through the first ionization energy of sodium, it's not going to be very much energy to remove that one electron because it wants to remove that one electron, right? So if sodium lost one electron, then that would make it act like it were here, like neon, because now it would have an electron configuration as neon. But if this goes to a second ionization energy, then that means that it is going to remove another electron, and it's going to remove an electron when it's stable and has a full 8. So if it did, that would put it right here. This would take tons of energy. Okay, well, let's look at this one too. This one, that purple box or blue-ish box, would be representing what element? That would be representing calcium. So if it goes through its first ionization energy and removes one electron, that would put it right here as if it were its electron configuration. If it removed another electron, that would place it right here as if it had argon's noble gas electron configuration. So this actually wouldn't take much energy at all compared to sodium, right? Because all I did was remove those outermost electrons, versus in sodium, I had to remove one of the inner electrons, and we don't want to do that. So right now, sodium is going to have that largest second ionization energy. Okay, if we look over here at that green box, we are thinking about sulfur. So if I'm looking at my green box, now sulfur has 6 valence electrons. It doesn't want to get rid of them, but if it did, one would be right here, the second one would be right here, because it never had to remove one of those inner or core electrons. It also is not going to have as much energy as sodium. Because on sodium, when we remove the first one, it didn't take a lot of energy. But that second ionization energy, I'm taking an electron away from a noble gas. I am taking an electron away from that full stable octet, or that noble gas electron configuration. And to do that will take a ton of energy. So my correct answer here would be sodium, or would be that red box. Okay, so trends in first ionization energies. As one goes down a column, it's going to take less energy to remove the first electron. So as we're moving down a column, we can see this on our graphic. In general, it's less energy. Why? It's less energy because we're adding more and more energy levels. And so if we're adding more and more space in between the outermost electrons in the nucleus, I'm adding more and more space. That means the attraction is weaker, so I don't need as much energy to apply to remove an outermost electron or a valence electron if the attraction is already weak to begin with. So it's not going to need as much energy. Generally, though, as one goes across a row, it's going to get harder to remove an electron. So we can see that the ionization energy increases as we go across a row or across a period. Why that happens? Well, it happens because as we are moving across, we know that there's more electrons and it's getting closer to becoming that noble gas configuration. So once I get around here by my nonmetals, where they're really just wanting to gain electrons instead of removing them, it's going to become harder to remove one, meaning it's going to take more energy, because these don't want to lose their electrons at all, because they're trying to become full with their outermost shell. There are two discontinuities, though, in this trend that we need to talk about. So the two discontinuities, the first one occurs between 2A and 3A. So first one occurs between 2A and 3A. So at 2A, we'd be right here, alkaline earth metals. 3A, we're over here, that boron family. And then the second discontinuity is going to occur between 5A and 6A. So 5A, they have it labeled here on our graph. 5A meaning that nitrogen family, 6A meaning my oxygen family here. So the electron removed is going to become farther from the nucleus. So there's also a small amount of repulsion by these s electrons. In terms of the s and the p block elements, they're going to show a larger range of first ionization energy values. Now, why do I see a discontinuity between 2A and 3A? What do you think? Why would I see a discontinuity between 2A and 3A? I want to give you just a second to think about it. Why? Okay, so the reason that there's a difference between 2A and 3A, because if I'm looking and comparing 2A and 3A, I see that 2A, it's going to take a lot more energy to remove those electrons than it would to remove that boron family. But why? Because remember, we said that in general, as we move across, as we are moving across a row or across a period, in general we said it increases. But if I look at beryllium, it's 899, boron's 801, magnesium 738, aluminum's 578. So actually between 2A and 3A I see a slight decrease. But why? I see a slight decrease here because beryllium has a full s orbital that's filled, right? So beryllium would be 2s2. versus boron is 2s2, 2p1. So because the third valence electron of boron is occupying the 2p orbital, that's empty for beryllium. So for beryllium, that, like we said, that subshell for the 2p is empty. It doesn't have that 2p subshell. So because of that, I'm going to see a slight decrease in my boron family, or my boron family here, that 3a. I'm going to see the exact same trend between 5a and 6a. I see a slight decrease in ionization energy as we move from nitrogen to oxygen. And we can see that because of my orbital diagram here. So let's compare those. Nitrogen has an electron in each of those orbitals, versus oxygen we have a pair in one and then two unpaired ones in oxygen's orbital diagram. Because we have a repulsion between that paired set of electrons in oxygen here, I see a slight decrease in ionization energy. So just because I have some extra repulsion here in oxygen, that's why we see just a small slight decrease in ionization energy. Whereas nitrogen, we have that one electron in each. It's simply because of this electron repulsion. That's the reason why I see some type of slight decrease in going from 5a to 6a. Now, when we talked about electron configurations in chapter 6, I don't know necessarily that we did the ions, but let's just be certain. So if I had calcium 2+, and I wanted to write the electron configuration for that, I know that calcium would be, let's do longhand configuration. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. If it has a positive 2 charge, it means it's lost 2 electrons. It has two more protons than electrons in its atom. So this positive 2 is indicating it lost 2 electrons. If I lost those 2 electrons, that would leave me with the noble gas configuration of argon. So I would take off that 4s2, and then I'd be left with the same noble gas that argon would have. You guys can write the rest of these, and if you have questions on this, let me know, but I think for the most part that should be pretty straightforward. Okay, we are going to start on Monday with trends in electron affinity, okay? And then the rest of the chapter, guys, after we get through electron affinity, is just properties of metals, nonmetals, and metalloids. So actually, the rest of the chapter is really just review after we talk about a couple more slides with electron affinity. So I will post your answers to chapter 6 and 7, actually I'll post them to chapter 6. I don't want to post them yet for chapter 7 since we haven't gotten all the way through chapter 7 questions, or all the way through chapter 7 PowerPoint. So I'll post the answers to the little multiple choice packet, and then I'm also going to put on some practice short answer questions for this. And if you have any questions, just send me an email or post on the blog, and I will see you guys on Monday. I hope you have a really great weekend. Bye!